Hello everyone, welcome back to part 2 of this video where we explore the basics of soundings and Skew-Ts. In part 1 of this video, I discussed how meteorologists obtain this data that's used to make these diagrams, and then I showed an example like this on your screen to help break down what is on a sounding and how to read a Skew-T. And then I showed what a sounding would look like back from a severe weather event. So if this is your first time watching or have not seen part 1 yet, you should go back and check it out. So for part 2, I'll take another look at the Skew-T and introduce temperature inversions and how they originate, and then discuss the different types of soundings and what kind of severe weather we can expect. So if you enjoyed this video, leave a like and subscribe, and we're going to get started. So first, let me define a temperature inversion. As we know, temperature normally decreases as you increase in altitude. However, there can be these shallow layers where the temperature actually increases, also known as a temperature inversion. So this layer acts as a cap on the atmosphere and will suppress deep convection. So that means that the air is not going to want to mix in between the layers, and so it's going to keep a lid sort of on thunderstorm development. This can also be called a stable layer because the atmosphere is going to be stable in that environment. So there are three main kinds of temperature inversions that we see here in the southeast, and those three are frontal inversion, the radiation inversion, and the subsidence inversion. So I'm going to talk about each of these and how they originate. So I'm going to pull some soundings from the Storm Prediction Center back from November 19th and the 20th, as this relates to the severe weather event that occurred in Mississippi and Louisiana back a few weeks ago. So first, let's talk about the radiation inversion on the 19th. This sounding comes from Jackson, Mississippi on the morning sounding. So radiation inversion results after a clear and calm night where surface temperatures will rapidly cool from radiational cooling. And so usually happens when you have, like, say, a high pressure system that is directly overhead. And that's kind of what we had in the southeastern states leading up to that severe weather event. So that's where the radiational cooling is going to be maximized. So you'll have clear skies overnight and a calm wind. So the radiation inversion is most visible on the morning sounding. And so it's going to be found mostly near the surface. So you see here on the surface, we have your surface temperatures and your dew point that are way down in the 30s. And then that radiation inversion is going to be followed by a rapid decrease in relative humidity. So your temperature and dew point lines are going to be rapidly decreasing or spreading apart from each other. And so all this warm air aloft here, that is what your radiation inversion is going to look like. And so this is due to the loss of daytime heating, and that energy is being emitted back into the atmosphere due to the loss of heat. However, a radiation inversion is less likely on a windier night and a cloudy night as well, because those two things will slow down the radiational cooling. This is because the winds will create turbulence in the atmosphere, and that will actually end up mixing down this warmer air you see above the surface. Will mix it down to the surface. So that'll slow down the radiational cooling, and also, if you have clouds overnight, those clouds will act as a blanket and will absorb the energy that is being released into the atmosphere, and it's going to re-emit it back down to the surface. And so that will also keep the surface temperatures a little bit warmer overnight. So the main idea here is that clear skies and a calm wind will generally have a radiation inversion in the morning. So now that is the radiation inversion, let's talk about the frontal inversion. And so to help illustrate that, I'm going to pull up a schematic here from weather.gov/jetstream. And so we're looking at the temperature advection from the warm front. So as we know, a warm front is a boundary between warmer air to the south, so warmer air over here, and then we have cool and stable air north of that frontal zone. And so our surface warm front would be situated across here. And so as we know, the warm air down to the south is less dense than the cool air up to the north of that frontal boundary. So when this warm air meets that cooler air, it's going to ascend above that cool, stable air down to the surface. So if we were to take a sounding, say either right on the warm front or just north of the warm front, say right here, you would have this shallow, cool layer down here at the surface, and then temperatures would rapidly warm with height, and then cool again as it goes above, as that warm air it kind of noses above that cool stable air. So that is what the frontal inversion looks like from the warm front. Now let's take a look at a sounding just to help illustrate this. So this is a sounding from Shreveport, Louisiana on November 20th of just a few weeks ago. So you can see here down to the surface we have, to give a little bit of context first, our warm front is situated somewhere across East Texas into western Louisiana, kind of right over where Shreveport is located. So you have your cooler surface temperatures generally in the 50s with dew point 51 as well. And then we have this sharp increase in temperature as you go up through the lowest 500 meters of the atmosphere, and then temperatures are going to cool again with height. And so this is what the frontal inversion looks like. You're going to have an increase in relative humidity as well, so your temperature and dew point lines will be closer together. And then you'll also have a wind shift associated with that temperature inversion. So here is where that inversion is located, right here. And then just below that, you have surface winds that are out of the south or south-southeast. And then winds flip back around to the west associated with that inversion. So that is how you locate the frontal inversion on a sounding. So now we've talked about the frontal inversion and the radiation inversion, and let's talk about the subsidence inversion. But before I dive into that, I want to recall the elevated mixed layer, or the EML. And so this, again, is hot, dry air that originates from the desert southwest that results from intense solar heating, generally in this desert southwest region. So in a severe weather setup, this continental tropical air mass is transported to our target region with westerly winds aloft. And so what happens here is that when these winds come off the Rockies and into the plains, they're going to actually descend into the Great Plains. And so therefore, the EML often creates a subsidence inversion, usually located between 1 and 3 kilometers. So another term to use to describe this process is a capping inversion, and this keeps a lid on the atmosphere and will suppress deep convection until the cap is broken or erodes. I'll talk more about this, how we break the cap, in just one moment. But now we're going to move on to the second part of this video, and let's talk about the different kinds of soundings that's associated with severe weather. So to illustrate this, let's revisit the severe weather event back on November 20th. And so these are the storm reports back from this day. And so we had a total of 17 tornado reports and about 50 severe weather reports, generally speaking, mostly a tornado and damaging wind event across central Louisiana and southern Mississippi. And so let's take a look at the 500 millibar map just to remind ourselves. So we had a pretty large long wave trough that was carved out through most of the central United States. And then you also had a pretty potent mid-level jet streak that was rounding the base of this trough here. And so that's indicative of a mature and strong storm system that is pushing through the United States. And this created this mass response down in the low levels. So this is our low-level jet at 850 millibars across the lower Mississippi Valley. So you see these winds here that are out of the south. They're about 30 to 40 knots or so. So this transported the warm, moist air mass ahead of the system to produce the severe weather. So this is the day 1 severe weather outlook from the Storm Prediction Center. And we had an enhanced risk of severe weather from about East Texas all the way to Jackson and even Hattiesburg, Mississippi. This is a level 3 out of 5 severe weather risk, mostly for a tornado threat, but also you had a threat of damaging winds across the lower Mississippi Valley as well. So let's see what kind of soundings that we had from this event. And this day had all 3 kinds of soundings that are associated with severe weather. So I'm going to start off with the Dallas-Fort Worth sounding at 6 a.m. So the surface temperature and dew point is 67 over 64 down here, and this is indicative of that maritime tropical air mass that was transported from the Gulf as a result from that mass response. And above this air mass, we have the capping inversion that was resulting from the EML. So here is our capping inversion right here in this layer. So this continental tropical air mass actually descended from the Rockies into the Great Plains, and that ended up capping the atmosphere, which prevented storm development until stronger forcing arrives. So how do we break the cap? Well, when you can either have a trough or a shortwave trough that pushes through, or you can have a front that will actually lift this capping inversion, lift it up into the atmosphere and cool it, and will that will cause the atmosphere to be fully destabilized, and then storms will be ready to develop by that point. So this gives the environment more time to be primed up for severe weather. And this creates what we call a loaded gun sounding, because the environment will be ready for a significant severe weather threat once storms are ready to develop. These are more common out in the Great Plains, Midwest, and occasionally in the southeastern states. So what kind of severe weather hazards can we expect with the loaded gun sounding? Damaging winds and large hail will be givens because of the large amount of instability, or the distance between the parcel temperature and the environmental temperature. So tornadoes are usually possible, but also dependent on the low-level wind shear. On this sounding, for example, we don't really have particularly strong low-level wind shear. And keep in mind, this is just a snapshot of what the environment is currently like, and not exactly indicative of how the environment is going to evolve. So you could, of course, have stronger low-level wind shear that develops later on in the day, and then this environment would be more favorable for tornadoes. But at least at 6 a.m., the wind shear or surface winds are generally out of south-southwest, and then you generally just have westerly winds aloft. So you don't really have strong change in direction as you go up with height. So directional wind shear is not particularly strong. So you would mostly just have damaging winds and large hail in this kind of environment. So moving forward through this event, let's look at the afternoon soundings and see what other kinds of soundings that we had. So this sounding from Slidell, Louisiana at 3 p.m. And we're going to look at the temperature profile first. So this solid red line here is our environmental temperature. And it looks pretty similar actually to the loaded gun sounding. But the main difference here is going to be this dry air that's in the mid-level. So when you have when our temperature and dew point lines are going to be spreading apart in the mid-levels, when you see it like this is indicative of a lot of dry air that is in the mid-levels here. And so that is the main characteristic of the microburst sounding. This dry air is going to get entrained in their downdrafts in your thunderstorms, and it's going to produce a lot of cool outflow. Low-level moisture also tends to be higher in these kind of soundings, which are most common east of the Rockies and particularly in the southeast. So we look here at the surface. We have a surface dew point of 70 degrees. So that is pretty high for pretty much anywhere, but especially in the cool season here. So the main hazards for these kind of soundings are usually damaging straight line winds due to the amount of outflow that's produced by our storms, but also you can get, under the right conditions, you can get tornadoes as well. And so now we're going to look to the north here, and at the same time period, at 3 p.m. So this is sounding from Jackson, Mississippi here. And we come across the third kind of sounding that's associated with severe weather. Looking at the temperature and dew point profile, this strongly resembles the inverted V sounding. So we call it this because these lines here that are highlighted look like an upside down V. And that occurs when we have strong daytime heating, and that mixes down the drier air down to the surface, and also warms our surface temperatures pretty rapidly. So we can also note the stronger lapse rates in the lowest 3 kilometers, or that's indicative of the rapid temperature change as you go up with height. Then look down here at the bottom left-hand corner, this box here, and we see here our low-level lapse rates in this first row right here. So that is an 8.3 degrees Celsius per kilometer. So that's pretty steep lapse rates. And this accelerates the thunderstorm downdrafts and makes damaging winds the main hazard. We usually don't see tornadoes with inverted V soundings because of the weaker low-level wind shear that's associated with this environment. And we tend to have straighter photographs as well. And then we also tend to have a lot of dry air here down at the surface. So you tend to not get as much tornado production out of your storms. So to wrap up this discussion here on these kind of soundings, I'm going to look at the lapse rates and compare them between each of these kinds of soundings. So the low-level lapse rates and the inverted V sounding will typically be higher because of the amount of daytime heating you're going to have. So that's going to warm up your surface temperatures the most, and so therefore you're going to have faster temperature change as you go up with altitude. If you don't have a whole lot of mid-level lapse rates, so the lapse rates here in kind of the mid-levels of the atmosphere are not quite as steep, so that's going to make your temperature difference between your parcel and the environment a little bit more skinny. So you're not going to have as much cape in the environment, and so you won't have as much hail production in your storms. You also tend to have less wind shear in this environment, especially down here at the low levels, so you tend to not get as many tornadoes. So going back to our microburst sounding, we can compare the lapse rates here. So the lapse rates on the microburst sounding are not near as favorable for severe weather. So there's not as much rapid change as you go up in altitude. Here, so looking down at this box here, these numbers here are generally about 6 degrees Celsius per kilometer, or even a little bit less. So that's pretty stable for the most part. You do have a lot of moisture down there in the low levels, which is basically what's generating most of the instability. And so damaging winds, again, are going to be the main hazard with these kind of soundings. And you could end up getting a couple of tornadoes if you have strong enough wind shear down in there in the low levels. In this environment, you do have pretty good veering of the winds aloft, and the increase in speed as well will generate potentially enough wind shear for a few tornadoes. And then we look at the Dallas-Fort Worth sounding back from the morning. And this is where you typically see the steepest lapse rates, generally in the mid-levels, above this temperature inversion. So you're going to have a larger amount of CAPE for generally for at least hail production. So this is what typically favors large hail. And then if the wind shear, of course, is great enough, then we could end up seeing a few tornadoes as well. And a significant tornado threat as well if there's enough wind shear in the environment, of course. So that's going to wrap it up for today. I hope you enjoyed watching, and I will see you next time.